Hi everyone, my name is Jurss, and this is my video presentation for the signature term project for DA5030 in fall 2025. Start with a quick overview of my dataset. I chose the breast cancer prediction dataset published by Vijayadithyan VG on Kaggle. This dataset contains the physical measurements of breast lesions in both men and women, as well as a target variable, which is a diagnosis of a benign or a malignant lesion. Malignant meaning it is cancerous, benign meaning it is not. The data also contains an identifier column for identifying patients, and then it has 30 continuous numeric features. These features encompass measurements about the breast lesions and things like perimeter, area, radius, and for all of the different features, it also covers the mean, the standard error, and the worst of all those. The data has a class distribution of about 63% benign and 37% malignant. The goal of this project is to create a machine learning ensemble that can accurately predict whether a lesion will be a malignant or a benign diagnosis based upon the given physical features. I explored the data in many different ways. It contains 569 observations of 32 different features, looking at it from a top-down view. Going into the features and the relationships, many of the features have strong relationships, and some of them, like radius and perimeter and area, are perfectly or almost perfectly linear relationships. The data contains no missing values, and the initial data had 211 outliers contained within 74 of the observations. There were no obvious data recording errors identified, so these outliers are true outliers and are going to be something that we'll have to deal with. Speaking of which, for the data preparation, I had three different models that I constructed: a C5.0 decision tree ensemble, a random forest model, and a bagged logistic regression ensemble. For the C5.0 bagged ensemble and the random forest, almost no data preparation was required. They're very robust outliers. There was no missing data to impute, and they make no assumptions about the underlying data. So I really just encoded the target variable to a factor and went from there. The logistic regression, on the other hand, required quite a bit of data preparation. The normalization of the feature distributions is one of the most important parts because that is an assumption of logistic regression models. As you can see with the histograms on the right, the top one is the raw data histogram for area mean, and then the second one is taking the log transform of that feature, which is what I used in the model. Most of the transformations were either log or square root, with only a few features not needing any transformations. A lot of these transformations helped reduce the outliers in the data, which I was very happy about because it's a pretty small data set, so I wanted to retain as much data as possible. However, after I performed the feature normalization, then I had to remove any outliers that remained because logistic regression doesn't like them very much, and they would be included in the C5.0 and random forest models, so losing that information for the logistic regression model will be kind of mitigated by the other two models. As I said, a lot of the features were extremely heavily related, and some of them even almost perfectly linearly related. So removing them to get address the multicollinearity was kind of not going to work. I at one point removed a bunch of them, and the more linear relationships kept propping up. So I performed a principal component analysis and derived the principal components, which I then used the top 10 to train the model. And of course, I had to encode the target variable for the logistic regression model as well. Let's take a brief look at the code for doing these transformations and preparing the data. Here's one example. I will run building a histogram for one of the features, compactness worst. As you can see, this has got a heavy right skew, so it doesn't look very good. And then I would create a test of a log transform. So I'd apply a log transformation temporarily and plot that on a histogram. And this looks much better than this. That right skew has been heavily reduced. Maybe there's a little bit of left skew now, but there's a very good chance this will be one of the outliers, and that'll help reduce it even more. But this is much more normal and much more acceptable. I would continue to do that for every single feature, and then compile a list of all of the features and their transformations that have been chosen. Made a copy of the data so that I don't mess with the original data, and just in case, always good to keep a copy of that. And then run this code to apply all the transformations listed here to every column. After doing that, of course, encode the target variable. After that, it's time to look at multicollinearity, which I run, and it creates a gigantic correlation matrix. So I filter out anything below 0.7 because it's not a very meaningful relationship, and so this way I can look at only what is. As you can see, there's a lot of very strong relationships, and there's even some, like these two, that are perfectly linear. So I decided to run this principal component analysis here to derive principal components and use those to train my model. So if we see view PCAres.x, we can see these are the principal components that were derived. There are 30 of them in total, and I will use the first 10 to train the model. Let's talk about the models that I built. I built 3 different model families to make up my final heterogeneous ensemble. I built a random forest model. This is great for capturing complicated nonlinear relationships, and the feature importance can be very helpful for interpretability, which is very important here because usually logistic regression would be great at that, but because we did principal component analysis, that makes it slightly less interpretable than it normally would be. The random forest is also going to help reduce overfitting of the whole ensemble, which is very important because I also built a bagged C5.0 decision tree model. These are prone to overfitting on their own because they're very high resolution and capture very specific relationships, right? They're very good at finding rare or specific patterns in the data that the random forest or logistic regression would just smooth right out. And when you introduce diversity with bagging, you really are going to be prone to overfitting the model. So that's something that's kind of balancing back and forth with the random forest to try and hit that, capture those specific relationships, but not focus on them too much when it's not necessary. The logistic regression model is also going to help reduce the overfitting because it's going to act as a baseline for all the linear trends in the data. It's got low variance, it's very highly stable, and that stability is increased even more via the bagging and bootstrapping that is being done. So that's going to really act as a baseline signal. So anywhere that the random forest and the decision tree maybe overfit at the same time, right? They overfit together in a certain area or certain relationship becomes very important to both of the tree models. The logistic regression is going to smooth it right out. All the models performed very well. The random forest model had a accuracy of about 96%, with a sensitivity of about 95% and a specificity about 97%. The C5.0 decision tree was very similar, an accuracy of 97%, specificity of 98%, sensitivity of 98%, specificity of 95%. And the logistic regression model surprisingly performed the best, with an accuracy almost 98%, a sensitivity of 97%, and a specificity of 98%. All these models had F1 scores above 0.9, so they had a very good balance between precision and recall. They're all very good at both predicting class and differentiating between the two classes. All right, let's briefly go over the code that I used to create these ensembles. First, starting off with the C5.0 ensemble, I created this function which trains all of the models and then also grabs their out-of-bag predictions and puts those into a list so that we can evaluate them using the out-of-bag validation. So when I run this, it generates a function here, and then here I can feed the input data to the function and the number of members that I want in the ensemble. So I started with a very low number, started with 5, and I could run it, and as you can see, then I produce a confusion matrix based on the out-of-bag predictions. So I increased that. In the end, I decided on 100 members as it was starting to become computationally more intensive, and between the 50 and 100 members, I was starting to see very diminishing returns with really small increases in F1 score and the other statistics that I was using to measure the model. I then trained the random forest model. This is much simpler. I just created a 80-20 split for training and validation, and I started with a 300 tree model. Estimated out-of-bag error rate here was 4.67%, which I was pretty happy with. After that, I decided to plot error as a function of the number of trees, and as you can see, the curve is flattened. After 250 trees, it's really flattened, so there wasn't much reason to go any higher than this in the number of trees. It might have even benefited from going down to 250. So I actually started with the logistic regression model by determining the global model because I wanted to just build one model based on all of the training data, excluding the holdout data set, obviously, just to determine which principal components were going to be the most statistically significant, and I performed backwards stepwise elimination of them until I got to the best model. This one was where it started to get worse. I went with principal components 1, 2, 4, 5, 6, 7, and 10 in the end. And then after that, this function here generates models and performs k-fold cross-validation on those models all at once. So I can feed the model the number of members I want for each fold and the number of folds that I want, as well as the input data. So running this with 5 members per fold, I can then build a confusion matrix based on the output of this. This outputs a list which contains the models, it's a list containing a list of models and also a list of the predictions. So this model is performing very well. I doubled the number of members per fold to 10 for a total of 100 members in the ensemble, and it ends up performing exactly the same. So I went with 10 members. More diversity is better than less. Let's discuss how I evaluated the models. I created an initial 80-20 split for training data and a holdout data set, and then every model was evaluated via accuracy, sensitivity, specificity, and their F1 scores. The random forest model was evaluated using its out-of-bag error estimation and via an 80-20 training validation set split, which I then turned into a confusion matrix and evaluated the model that way. For the C5.0 decision trees, I generated out-of-bag validation during the bootstrapping. This way I could avoid any data leaks and make sure that the models were only being validated on data they hadn't seen themselves specifically. And that gave us our full output for that ensemble. And I took a similar approach with the logistic regression ensemble, also 80-20 trained validation splits, but this time with 10-fold cross-validation with bootstrapping, similar thought to the decision trees, where I really wanted to make sure I was evaluating the ensemble members on only data that they hadn't trained on. And finally, we come to the full ensemble model. It's a blended heterogeneous ensemble of the 3 models that we previously discussed. So I would get the outputs from the homogeneous ensembles from the C5.0 trees and the logistic regression models, which were also blended. And then I would get a probability from the random forest model. And I would blend them by taking the mean of all those probabilities and converting it to a class. This allows each model to smooth the other models out and influence the final decision more than something like majority vote. If 2 models were overfitting in the same way, for example, the logistic regression and the random forest model both predicted a low probability, but the C5.0 tree had some high resolution relationship that was making it predict a high probability, then majority vote, it would be labeled as a 0 event, whereas perhaps taking the means, it could push it up to a 1 outcome, depending on the actual probabilities from all 3 of the models. I validated the final ensemble against that holdout data set, as previously discussed, and I assessed it in the same way as all the ensemble members, overall accuracy, sensitivity, specificity, and F1 score. It performed at a similar level to most of the ensemble members, outperforming the 5.0 decision tree and the random forest quite nicely, and performed almost on par with the logistic regression model, but it had a much higher specificity. That model actually had a 97% accuracy, 96% sensitivity, and a 100% specificity when checked against the validation set. In summary, the heterogeneous ensemble was composed of 3 individually validated models: a bagged C5.0 decision tree ensemble, a bagged logistic regression ensemble, and a random forest model. The final ensemble outperformed the individual models and combined their complementary strengths of the member models very well. This resulted in a high sensitivity and specificity, showing a strong balance of high predictive power and good discrimination between the classes. I think I have managed to create a very stable and powerful predictive model here. Some key lessons that I learned: model diversity is key. Multiple models that work differently and see the data differently can help reduce variance and produce highly stable ensemble models. Bagging improved stability immensely, especially with small data sets such as this. Bagging is an essential tool. And finally, holdout validation was an essential thing. I actually started without a holdout validation set, and wasn't sure at first how I was going to train the models effectively until I went back to create the validation holdout set, and that way I could avoid data leaks and really make sure that my real-world predictive power is accurate. Thank you very much for listening. I hope you enjoyed. Have a good rest of your day.